the most boring talk title in the whole C++ and C roster, but still people come. That's very nice. Thank you very much. If perhaps you expect some very like high-end, bleeding-edge C++ code today, that's not what this session is for. We're going to try to get back to basics a little bit and perhaps refresh all the knowledge we have on special member functions in C++. Or perhaps even learn new things today. I'm trying to be comprehensive, so I bet there's something for everyone. So let's see what we're going to see today. So I split up this talk in 4 parts. First, we'll look at the fundamentals, like start with ground zero, such that we're all on the same page for the rest of the content, which will be partly about the declaration rules. Who has seen this talk by Howard Hinnant on I think it was on move semantics generally. It's a bit of an old talk already, more than 10 years old, I guess. It shows this table. I'm quite sure most of you have seen this table where we have all the user-declared member functions and then the compiler implicitly declared member functions. Well, I'm going to cover that table as well because it's the best way to cover this material. But we'll look into that and also how to practically apply the rules that are in this table and how to remember the table, because you can print it out and put it above your desk, but then it's still not in your head. So, and actually the rules are quite easy to remember if you get to it. Then we'll look at some implementation guidelines for some of the special member functions. I don't have the time to cover everything of this. We have 90 minutes or a little less, but still such a vast subject, like any subject within C++ is, that we can't cover all of it, but we'll try to make a good job of it. And then if we still have time, which I'm not sure today with all the stuff going on, before we can go into some more philosophical subjects on this topic. Like, do we even need special member functions? Why do other programming languages not have special member functions, and how do they deal with all this stuff? Right. Now, a little bit about me. I'm Kris. I work in a computer vision company in Eindhoven in the Netherlands. We make products, systems, embedded systems that take in video and then do traffic analysis on it, things like that. And we make most of our code in C++. We use a lot of machine learning algorithms, and it's a fun business. Outside of work, I do a lot of other things, amongst which is also training these days. So training for fundamental level C++, which is quite a challenge these days with all the stuff going on in the language. If you want to contact me, you can do so via email or LinkedIn. Right. Now, before we go to section 1, a little premise and glossary. I use C++20 code throughout the presentation. This is a conscious choice. I think after 3 years of standardization, we can, or most of us I hope, can use C++20 in production, or at least in a part of production, unless indicated otherwise. So that's that. Then also, just to save some slight real estate, I abbreviated some terms, like special member function gets old really quickly if you have to repeat it like 100 times. And then we have the regular abbreviations for constructor and destructor. I also considered abbreviating assignment using the first 3 letters, but it's perhaps not a good choice for a serious conference like this. So, right, the fundamentals. Let's really start at ground zero. What are special member functions even? Why are they called special? What is special about them? We all know member functions, but what makes them special? Well, special member functions are special because under some circumstances they can be generated by the compiler, even if we don't explicitly ask the compiler to do so or define it ourselves. Sometimes the compiler is able to generate them completely for us. And that makes them special. But to fully get this definition, we must also look at what is the difference between declaration and definition. Because if you get more into the nitty-gritty details of language design and rules, it does make a difference if we talk about declaration or definition. Don't mix up the terms if you want to be precise. So a declaration is simply just an introduction of a name into the program. Nothing more than that. It's just the introduction of the name. And then a definition is a declaration including adding value to this name. So then the introduced name also has a definition as a whole. So for a function, that may mean also that the code is there for the function. And for a variable, that means that the variable has a value as well. So this means that the compiler is not only able to generate the special member function name, but even the part that makes up the function itself, so the code behind the function, is also possible that the compiler generates this for us. Some simple examples of declarations versus definitions is this. So on the left we have declarations only, and on the right we have the definitions. But I think that's clear now. So let's see what is this magic of special member functions. So if we would build the code on the left here, we have the most simple class definition that we can ever make. And then we use this class type in various ways. We construct it, we copy construct it, we copy assign it, we move construct it, and we move assign it. And in the background, the compiler will make all this fancy stuff that is on the right. So what it will do, and you can check this out yourself on CPP Insights. It's a nice website to experiment, I think, sometimes. And what the compiler will do is it will magically serve us with this definition of the interface for class X without us having to do anything. So that's really nice. So we get a lot of presence, basically, from the compiler for free. And this is also very important just to remember, even if we don't do anything, we do nothing, we get a lot. So keep that in mind, because it will come back later on. But it's also really easy to break at least part of this magic. Here we get everything, but of course this class definition is really poor, so there's nothing in it, very useless. But suppose we make some kind of class that actually contains data, then suddenly parts of the magic is gone. So in these three examples, each of them has their own reasons why the part of the magic is gone. But at least for all these examples, it holds that they are ill-formed because the compiler is not able to generate the required special member functions for us anymore. And we will get a compiler error. So on the left, we have a constant value. Well, obviously it makes sense. If it doesn't have a value, then how is the compiler supposed to generate a default constructor that constructs this value, but there's no value for it. So, and the same holds for the reference. A reference needs to be bound at initialization, and that's not there yet. And on the right, we actually declare a custom constructor, but we want to do default construction. So the compiler is just backing off and saying, no, you just said this is the way you construct this class, but I don't know how to do it by default. So how does this work? And what functions do we actually lose, really? Well, that is what we are going to find out today. Because there's actually some very logic rules behind all this. Now, we can fix these examples quite easily by either implementing like a constructor that we need to actually assign a value to either one of the examples, or we request a default constructor from the compiler, and then we're fine. And for some of these examples, especially the leftmost two, we also still lose some of the magic, because the assignment operators, they are not there. And why is that? Well, look at this specifier and look at the fact that this is a reference. Of course, you cannot rebind a reference. So once it's bound, it's there. So there's no default assignment operator. Right, now what are the options for us if we want to fix a class for which we don't have the compiler-defined implementations? There's actually, in general, there's only two options. We can either do nothing and have the compiler generate it for us, but then that must be possible, of course. Or we user declare the special member function. And that is possible in 3 different ways, and they all count as user declared. We can, of course, create a custom implementation. This is the most obvious way to user declare a special member function. But we can also request a default implementation from the compiler or delete it. And even deleting a special member function counts as user declaring it. And we'll get into that in a little bit more detail later on. But just remember, if anything we do with the special member functions, it counts as user declaring. Because this is really important to understand the table that we're going to look at in the next section. Then what is this magic made of? If we request a default implementation or we delete it, what does that mean? What is the compiler going to do? Is it going to use ChatGPT to generate a special member function? Well, of course not. That would be silly. What it will do, it will just sort of recursively, in order, put the corresponding action on all the non-static member variables of a class. And that is what happens if you do default definition of a special member function. And if you delete it, and this is important, the corresponding special member function will be declared, right? So the name will be introduced, it will participate in overload resolution, but it will be marked as unusable. And this is a little detail that will come back in the table in the next section. So it will be there. It will only be not fit for use. So that's the rule. Right, now, some more fundamental stuff. Of course, class lifecycle is defined by the constructor and the destructor. We all know this. But these are all the prototypes of the special member functions in a class. And of course, this is stuff you should remember as a C++ programmer. And if you've been in the business for some time, you will get this from the top of your head. And then let's cover each of them. So if you are going to dive into constructors, you will see that in literature or on blogs or whatever resource you're consulting, there will be a lot of talk about all these kinds of different constructors. We have context constructors, inheriting constructors, default constructors, non-default constructors. You could almost play bingo with all the types that there are. But actually, it's not that complicated as it seems. There's only 4 types of constructors. That is either the default constructor, any non-default constructor, we have the copy constructor and the move constructor. All the other types that I just showed in the previous slide, like constexpr, they're all simply adjectives, like properties of one of these classes of constructors. So don't be fooled and kind of like puzzled with all these terms that are going around. It's only these 4 that are there. Obviously, well, the default constructor is called when we call a constructor without any arguments. It makes much sense to have a type have a default constructor because it makes a type really easy to work with, especially if you are writing libraries. And any non-default constructor is, of course, any constructor that is not the default constructor, which is a funny definition, but still, it makes sense. And technically speaking, the move constructor and the copy constructor are also non-default constructors, you could say. Right. What happens if we have a constructor that is a non-default constructor, but it has default function arguments in the definition? Well, then it counts as a default constructor because it is able to take the place of the default constructor. If we have this example here on the left, where we have 2 separate constructors, an explicit default one and a non-default one, and we can create this point like this, then it's sort of equivalent to this. So this constructor here, which takes the default arguments for x and y, is actually counts actually as a default constructor. But this class, I don't think it's really good in any way, because it also allows us to create this point with only providing value for x, which doesn't make much sense. I'm not a great fan of default arguments for functions in general. I'm not sure how your viewpoints are on this, but well, that we know it. Well, the destructor, of course, destructor is called when a lifetime of an object ends. It can be either by scope, if we have automatic variables, or in this case, when we have dynamically allocated an object and we delete it. Then we have the copy operations. We take an other object by constref, and then we can copy it. Well, we all know this. It's probably not much more to say about this. Then perhaps if you've not been too busy with move semantics, then this is perhaps a bit new, but still move operations are very similar to copy operations, but they operate on non-const R-value references. So never put const here. It's always non-const R-values. And with that, we can basically copy R-values around, which is called moving in C++. Right. To finish this fundamental section, let's look at how the special member functions work in the context of composition and inheritance. And to do this, I often use this funny type, something similar like this, in Compiler Explorer, and I'll just whip up an example, and I use this as a tracer to see whether my type is being copied or not, if I'm creating a container-like object or something, and I'm just trying to figure out whether all the dealing with objects is done right. And we can use this to also like figure out stuff like this. And of course, most of you know this, but just for the sake of being comprehensive, we're going to repeat this. So if we have a composition of an object type here, and it has a member, non-static member of type member, of course the member will be initialized first, and only then will the type be constructed, which perhaps on a first glance doesn't make much sense, but the type has to be finished before it can construct itself, of course. And we can check this, and it then looks like this. And the same holds for inheritance. So first the base class is constructed, then the derived class. But now what if we combine it all? What happens now? Can anyone shout the answer? Or?
Base first.
Base first, and then?
Then the members.
Then the members, and then the derived, obviously, because It's the only one left. Yeah, so that's correct, indeed. I always tend to think of it as a more like layered system. So you have the base layers first with all the members, and then we come at the top layer where the type is, and we have the members and then the derived class. So, of course, the derived class will be initialized last and destructed first, because it's like the most final thing to do. And then first we have base and then the members. But honestly, if you would ask me this like 5 years ago, and I was almost 20 years into my C++ career, I wouldn't be like 100% sure about the first two orderings, honestly. Well, perhaps it says more about me than about C++, but still. Right. And also, of course, this holds too if we have more a base class. If we have multiple inheritance or inheritance relations that go further down than one level. Right. Now that we have all the basics out of the way, let's move on to the declaration rules, because here's where most knowledge is, I guess. And again, I'm going to use some content of Howard Hinnan's talk, because it's just very good content, and I think it's very useful. So I think many people, when they think about the special member function relations and all the rules that are there, they have a bit of a labyrinth feel for it, because it's just sometimes it's this, sometimes it's that, and they don't have a real like framework to keep all the stuff straight in their head. And that's why we're going to look at it using this table. And this is actually the same table. So thank you, Howard, for creating this. And the idea is here on the rows, we have all the user-declared special member functions. Remember, user-declared means either custom implementation, default requested, or deleted. It all counts as user-declared. And then on the columns, we have what the compiler will then be able to generate for you. So basically the presence that the compiler will get you. Now, of course, the first 3 rows are not really surprising, right? I mean, if we do nothing, we get everything. If we define any constructor, of course, the compiler is not able to generate the default constructor anymore for you because, well, you just said that construction of this class is special. Why would I be able to generate it? And of course, then if we define the default constructor ourselves, well, the compiler doesn't have to generate it for us anymore. But it can still generate all the other members. But at least what we should take out of this is that this first row, if we do nothing, it's like the best scenario, right? I mean, then we get everything else for free. So if we are able to achieve that at least, that is I think, a good goal. But things become more interesting once we get to the next row. So if we user-declare the destructor, we basically lose the move operations. In a sense, move operations are also destructive, right? I mean, we move some object to another one. So basically, the moved from object is well, left in a moved from state, which you could view as a destructive state. So the reasoning behind that is, of course, the compiler has to be conservative. So if you assume anything on the destructor, then the compiler can't anymore. Makes sense, right? Now, for the copy operations, if you define those, then, well, obviously, if you define the copy constructor, you lose the default constructor. That does make sense. But also, we lose the move operations. And also, that makes sense. Because if we are user declaring that copying is somehow special for our type, then what is the compiler going to know about moving, right? I mean, it's not able to It's not going to be able to do any assumptions on that. But the real interesting part is when we user declare the move operations. Again, for the move constructor, we lose the default constructor, which also makes sense. But then there's something weird going on, because right now, if we go back to the copy constructor and we declare that, we still get the move assignment operator or the copy assignment operator. Why is the compiler even going to assume something about copy assignment if we declare the copy constructor? Well, there's a bit of historical reasons for this. I'm going to come back to that in a couple of slides. But they didn't do that for the move operation. So if we declare either move operation, be it the move constructor or the move assignment operator, we don't get the other one. And this also speaks for always create the copy operations or the move operations in pair. So never split them. It's just weird, right? And also the compiler is just going to treat us as if it should be. But then there's another patch here, which is these deleted annotations. If we user declare the move operations, we lose the copy operations. And again, this makes sense as well, but now we don't get them not declared, but they're actually deleted. So that sounds a bit more strong. And in fact, it is, because again, what is the difference between not declared and deleted? If we don't declare, or deleted members still participate in overload resolution, right? So they were declared, but they are marked as unusable. If a member is not declared, it's just not there, as if you did nothing. So we are left with this table. So you can, again, print it out, put it above your desk or your bed if you're really desperate. But how are we going to remember all these exceptions and this whole table? It's just too much information, bless you. My strategy, and I think it works for me, is just try to remember the exceptions in this table. So we notice that it says defaulted almost everywhere. But it doesn't say defaulted in the constructor column and for the move operations mainly. So how can we make sense of this? Well, what we'll do is we'll create 3 separate rules. So we have one rule for the default constructor. We have another rule for the move, for the copy operations. In the case we user declare the move operations. And we have one rule for the move operations in general. And we'll put that in our head, because that's only 3 sort of general rules that we have to remember. So if we declare any constructor, we lose the default constructor. That's easy to remember, right? And it makes sense also. If we user declare any copy or move operation or the destructor, the move operations will not be declared. So they will just not be there. And then lastly, if we user declare any move operation, we basically have the copy operations deleted. And I actually remember these more easily like this. Perhaps you do as well. I don't know. But this is my sort of fake notation, pseudo notation for remembering this. And this makes it much easier to remember than this whole table with all the columns and rows. Right. Another thing that is quite important is the declaration rules are transmissible. Because we just looked at this table, which is nice, but in reality we have inheritance hierarchies, we have composition. How do these rules interact then between the types? Well, the declaration rules in the table, they just hold for one like insular type. But actually the declaration rules are transmissible, so every type has their own rules, basically, and the compiler has to like combine them and make the strictest rules hold for the eventual result. So that's how they combine. So basically, for instance, if we have a base class that contains a standard mutex, which is an immobile type, it's not copyable and it's not movable, then it doesn't matter how nothing we do in the classes above, it will not be copyable or movable because we just have this type in ourselves as well. So that's how this works. Now let's make everything a little bit more interesting. Consider this example here. So we have a class that user declares its copy operations, right? And that's the second rule. So we lose basically the declarations of the move operations now. So, but then we are going to use this type and then, let's move construct another type from this existing one. What will happen? Well, in the background, it will still copy construct. Now, how is that? Well, obviously, when the language designers created move semantics, they had to keep into account all the backwards compatibility that's in the language. And they couldn't just have all the code that didn't have move operations basically fail. So what they decided they would do is make this table not like this, but like in reality, it's more like this. So what we get is we get basically a fallback from move operations to copy operations without you noticing. That's why it's sometimes really important to do these tracer types or do more performance analysis to see whether your types are actually being moved or copied for real. But that basically makes any operation that falls into this 6-block category here fall back on copy operations, if it is possible. But there's more, because as I just stated, right, the committee is very conservative these days. So if we define either one of the move operations, we lose the other one, which of course makes a lot of sense. But they didn't do that back then. They still have, if you create the copy constructor, you still get the move assignment or the copy assignment operator, which is a bit weird. But we have to keep in mind that the table used to be like this back in the day, and they had to basically tack on all move semantics onto the table. So that's why it works like that. Right, but that makes it easy at least to port legacy code, because we get copy behavior if we move types that didn't have a move operation declared, even though it was required to, because here in this example, we user declare the destructor, and we basically lose the move operations, right? But still moving does work, or it does work in a sense that it basically fallbacks to copying. But if we want optimal performance, in this case, for example, here we have an R value that in pushback it has an R value reference overload. It's this one. So why is it not using that one? Well, because we don't have the move operations, right? Because they are not declared because of our custom constructor, or destructor, sorry. So the only thing we have to do is implement the move operations, and now this code will work properly. But of course, we have to take into account that if we implement the move operations ourselves now, we get into another rule, and basically we get the copy operations deleted. So if we want to restore copying as well, we have to implement those as well too. But that's just following up the rules. Well, enough of this table and the details. How can we actually use these rules in a production environment. I mean, we all have colleagues, and they also have to work with these rules. And we cannot assume everyone to just remember this whole table, and it's not really practical. And for that, there's the rule of X. In my research for this talk, I found many exotic rules, even some kind of weird 4.5 kind of things. A lot of it dates back from the time when we didn't have move semantics. Like the rule of 3, it did make sense when Scott Myers made it up. I think it was him that did it. And he was no slouch in the C++ community. But during that time, there was no move semantics. So there was only like 3 special member functions that counted. But there are other rules that do make sense still. So how can we make something useful out of this? Well, let's start with the rule of 0, right? Remember those first rows in the table, and also the very first example that I showed. If we do nothing, we get everything, right? Or at least if our types also all the way down do nothing, then we get everything for free. So that's the first rule, and it's actually really usable. And basically what happens is, if suppose we have a vector in our class, then we just lean on the default behavior of the move operations of a vector. We basically use the implementation that the standard library implementers made for us. It's probably much better than what we could achieve in the first place. And now, then what I do, at least in my company, I've been using it for almost a decade, I think. We basically define a couple of classes, and I'm following Jonathan Muller's suggestions for that. He wrote a nice blog post on this, and he defined 3 class categories that are eligible for like custom implementations of these rules. So we have 3 classes. So there's the category of wrapper or container classes. There's the resource managers that come up quite often, at least in my area of expertise. And then we have the more rare type, that is the immobile class, like standard mutex, which is either immovable and incopyable. So that's why it's called immobile. And then for all the rest, we just use the rule of 0. And this makes reviewing much easier, and also just as a company guideline, this makes much more sense. Let's look into each of these. So obviously, a container class must be very flexible. It must be usable in any situations, deal with each contained type properly. So probably you're going to have to implement all of the special member functions. And also try to keep them no except if you can. Then we have the resource managing classes, and this is a category, it's a bit vague perhaps, but what I mean with this is we have some resource, and most of the times it's something like a hardware, like a GPU or a memory mapped hardware device, of which there's only one, and we're defining a handle to this memory resource. It doesn't make sense to copy this resource because there's only one physical resource actually. And these are basically move-only types, so uncopyable. Think of something like a unique pointer to some resource. It's move-only as well. Or a thread, or a JThread these days. And then only define the move operations yourself if you have to. And the compiler will take care of the rest. Right? By the rules, what it will do is, of course, it will delete the copy operations, so we don't have to do that explicitly. And then for the immobile classes, we just delete the copy operations, and then we don't get the move operations, obviously, right? That's the second rule. And we're fine. We don't have to deal with this in more detail because the class is immobile, so we prevent any ill use later on. And again, here we basically lean on the compiler to do the rest for us. Then if this is still too complicated for you or your colleagues, I can't make any assumptions on your colleagues. You can deal with what is called the rule of 0 or all, and please note I'm using all because perhaps in the future we get a rule of 7 or 8 or something. We get something more fancy than move semantics even, and then the number is off. So in this case, all basically means everything, like the container class. So, but this is already very useful for review. So if you encounter a review and someone's making a custom type and does either nothing or all of it, then you're fine. But you're triggered if they are using some kind of mixture, so they only define the move operations. Then they really need to have a good story. Why are they doing that? But this already helps. And then at least you're safe. Perhaps you're not performance optimal, but you're safe. And of course, then the trigger is the second rule where you have a custom copy constructor or copy operations, move operations, or destructor. Right, some last notes before we go into the next section. I mentioned this already. Try to have a default constructor because it makes types much easier to work with. You can basically already reserve vectors with a size and things like that. Never split the copy or move operations. That's almost always a smell, I would say, a code smell. And then lastly, don't explicitly build types that are only copyable. I guess there are some use cases for it, but most of the time it's just weird because people will be trying to optimize their classes using your type, and then they are constantly like figuring, why is it not working? Why is it not movable? And that's just weird. Right, that finishes the declaration rules section. Let's look into some guidelines on how to implement the special member functions. Before we do that, I'm just going to re-show a slide from earlier, which is what are the options again if we are going to implement special member functions. Well, we can do nothing, which is by far obviously the cheapest way, or we can use declare it by either custom implementing default, requesting a default from the compiler, or requesting the compiler to delete the function. Now, for the constructor, and by the way, consider this as a sort of checklist for your own use. We're not going to dive into every detail that I'm going to show here, but obviously use the member initialization list. Probably you all know why, but still, it is something to look out for. Never call virtual functions from your constructor or your destructor. Right? Remember the hierarchy of construction and destruction. If you're calling, if your class is going to be a base class in some kind of inheritance hierarchy and you're calling a virtual function, then perhaps during construction time, your derived class has not been constructed yet and it will do all kinds of funny stuff. And also, conversely, when you're calling a virtual virtual function during destruction, perhaps already the derived class was destructed before you because you're more deeply into the inheritance hierarchy. And, well, that makes sense, but there's no one preventing you from doing this. And so we have to like be disciplined, to use Sean Parent's words, to do this. I don't know if there's any static analyzers able to figure this out. I guess so. But then, obviously, and make sure your object is in a specified state after default construction. It's a bit of an open door, of course, but it also holds for objects in a moved from state. So we'll come back to that later as well. And then always, or try to mark a constructor taking only one argument explicit. And why is that? Well, because if it's not explicit, it basically allows implicit conversions to happen in your constructor. And this can lead to code that is sometimes not really what you wanted. For example, here, we have this class here, and it takes an integer, a signed integer, as a constructor argument. And we have a function using this class as an argument. Then we were able to call this function directly with a signed integer. But I don't know about you, but this looks really fishy to me. I mean, it's nice that we can do all these implicit conversions, but as a general rule, I think they are a bit evil. And I like the more explicit case like this. So we make the constructor explicit, and now this will not be accepted anymore because it's a signed integer and not a type fort, and now this. Right, so we basically force everyone to use it. Now, why should we use the member initialization list? Well, most of you know this, of course. But what happens if we do this? So we basically, in the body of our constructor, assign the value directly, like this. Well, we basically get two operations. We get a default construction of value, and then we get an initialization. And this would be a direct initialization of value. So that saves us some operations. So it's more efficient. But then we have those C++11 default member initializers. And I think, at least for some of my colleagues, they made the world nicer in some ways, but also more confusing in another way. Because what happens here in this case? So we have a class that has two values, both of which have a default member initializer. And then we have a constructor, a default constructor that only initializes one of them. What happens? Will value 1 be initialized twice, or what will happen here? Does anyone know? Well, at least we hope it doesn't work like that, and it doesn't. So value 1 will only be initialized once. Probably this one is leading, and this one is not used. So this default member initializer here is not used. But what happens to value 2? Because it's not in the member initializer list here. Will it be initialized even at all? Yeah. So in this case, the compiler will use the default member initializer. So we can really, well, make this situation very simple by basically removing the whole constructor, because we already have the default member initializers. So the default constructor, the custom default constructor, was not necessary at all. Now, something to note regarding the initialization order in a member initialization list. This is pretty evil code, if you ask me. But so we still have this class with two values. And now in the initializer list, we basically initialize value 2 first, even though value 1 was defined first. And then we even initialize value 2 in terms of value 1, even though it's not been initialized yet. And this is just accepted if we don't turn the compilation compiler warning flags properly. So really keep in mind, turn on all those warning flags if you can, and look at them, right? I mean, if you're really obnoxious like me, you just use w-error or w/x, basically force everyone to fix their warnings. right? Because evil things can happen if you let code like that through. Right, now, some guidelines regarding the destructor. Of course, again, don't call virtual functions from the destructor even. Make it virtual if applicable, and perhaps most of us also know why, of course. Then never throw exceptions from destructors, right? So why do we want a destructor to be virtual? Well, obviously, if we would use a base class pointer to a derived class, and we would we would destruct the derived class instantiation here from the base class pointer, if we don't have a virtual destructor, then only the base class destructor will be run and not the derived class destructor. We get splicing and all kinds of stupid stuff, memory leaks perhaps. So make a base class destructor virtual. But also tack on this override specifier on the other side. Because if you don't do that and you leave out this virtual here, now because of this override specifier, the compiler is going to complain, yeah, you put override on a base class function that's not virtual. And the other way around, if you have clang tidy or some more strict compiler rules or flags enabled, if you forget override, then the compiler is going to complain as well. So it's basically a two-way like safety mechanism. It makes much sense to put them on both sides. Now, why shouldn't we throw exceptions from destructors? Well, obviously, perhaps our class is being destructed because of another exception that was going on in the scope of this object. So there is already an active exception. So what would throwing an exception even mean in that context? So we have multiple, we have an array of exceptions or something. How to deal with that? So the way out is basically the terminator will come by. If you, by the way, if you're interested in dealing with exceptions during destruction, it is possible because you can look at the active exception by using a standard uncaught exception. It's a bit of a, well, I would say a clunky, blunt instrument, but it is actually useful if you want to create something like transactional rollbacks or something, and you want to make sure you clean up properly after your object is going away. Now, for the copy operations, we have a bit of a longer list. It's generally, well, a bit more complicated to implement these properly. Obviously, we have to always copy all parts of a class. Makes sense. Perhaps use tricks like standard tie to like create a tuple of your member variables. If you've ever seen the talks by Sean Parent on Better Code, he uses this trick sometimes. And it makes you not forget copying or moving parts of your class. It's really useful. If applicable and needed, call the base class. Sometimes you need an alternative constructor for your base types. It's something to keep in mind. It's not always necessary, but sometimes you have to. Handle self-assignment, one of those weird corner cases in C++ again. It allows you to do self-assignment, so you have to deal with this, right? You get funny behavior if you copy yourself into yourself without checking first. So. And the same holds for moving, by the way. Always return a reference to this, and you may even think like, is it possible to not do this then? Well, yeah, you can create a copy assignment operator or a move assignment operator even with a void return type. It's fine. The compiler is fine with that. But then in C and also in C++, assignment is an expression, so it should result to some value. And then you can do chaining. A is B is C is D. I'm not saying you should because it's weird, but that's what everybody expects, right? So return a reference to this. Then obviously provide strong exception safety. So if something goes wrong during copying, be sure to deal with that properly. And then lastly, mostly for performance reasons, stick a no except on your copy operation if it's possible. So I would say be a bit conservative with that because it's mostly performance related. But so the move operations list is almost the same except for the last line, which is leave a moved from object in a valid state. And this really is the same state, in my opinion, as a default constructed state. I always make a point of it in reviews that moved from state should be at least almost the same as default constructed state. Because in C++ we can do moving and then from an L value and turn it into an X value and have it be moved like this. And then use an object even after it's been moved from, right? So suppose, and this may feel a bit contrived, but I actually saw this in real life. Suppose we have some resource managing class. It is move only, but it keeps the resource separate from some administration to flag basically whether or not this resource was initialized properly or not, because it's for some reason we split the resource allocation from the resource initialization, but we have to keep this administration separately. But now if we move construct a type, so I implemented both the move constructor and the move destructor, or move assignment operator. I'm really getting puzzled by all these terms. But I forgot something. Because here on line 10, we take A, which was created, it was properly initialized, so during initialization, probably this initialize flag was set to true, and all was fine. And now we're moving A into B, and we leave A in a moved from state. But that means that we also have to reset all the administration stuff that was going on in A. So right here, the post-move state of A is invalid because even though the resource was moved, so the unique pointer is null, so the resource is gone, it's in B now, but the administration for the initialization state was not moved or reset properly. So this should be fixed by this line, and of course the same line is in the move assignment operator. And now the post-move state of A is okay. And it's basically the same as the default constructed state. So that's why it's important. And it's a bit, the fact that we in C++ don't have this borrow checker, the compiler will just have us have objects in move from state that is incorrect. And it's just up to our discipline to fix this. Right, a couple of fringe subjects for this section. We probably all have heard of REII, right? This is a term that's coined now and then. Who in here didn't hear of REII ever before? Well, all of you know it, right? So then you probably also know what it's about. Obviously, it's very closely tied in with special member functions because basically it uses the constructor and the destructor as a sort of event hook to do stuff. But it actually is really useful as a pattern for your custom classes. And in the standard library, there's numerous classes that use this. For instance, the lock guard obviously will, during this part of the code, will lock the code upon or lock the mutex upon construction, and then unlock the mutex upon destruction. But the nice thing, of course, is that we don't have to put any additional code here. We simply use the fact that log is an automatic variable, and we'll go out of scope here, that it's all underneath the covers the locking and the unlocking. But it's actually quite useful in practice as well. And just some examples. Suppose we have some kind of secret store called a vault. And during our operations of our program, we want to access this vault and take out some secret for a limited amount of time. And we, of course, want to limit this time frame to keep the program safe. My talk is about safety now as well, I guess. So, cool. But now, by using this additional class called Vault Accessor, we can automatically limit the scope of the access, which is quite nice. But this can also be useful for something like temporary files or directories. Suppose you have you want to have some temporary file to write scratch data to in your code, then you can create an RAI, or as I would like to call it, constructor destructor pattern class that basically creates the file during construction and then removes it completely during destruction, and you can use it in the meantime. And all the cleanup, everything is in the type itself. It makes for quite nice code. And once you take notice, you will see this all over the place. Then some last notes on testing. Because are you testing your special member functions? I think you should. And the least things that I always include in my test suites is things like this, like try to provoke all the special member functions being generated and in the test code. Have all the sanitizers on in these tests and run static analyzers even. But also the compile time guarantees. And this is something that Howard Hennant also mentioned in his talk. Like, test and guard the compile time guarantees of your special member functions, so basically of your class types. Do they still copy properly? Do they still provide like this no-throw construction guarantee? And there's a couple of examples here and also in the next slide where I use basically types from the standard library to illustrate these tests. And I think they are really useful because once code is written, it will be refactored at some point in time, and people will just not notice that they kill behavior that was intentionally there in the first place. So this is really useful for CI. Right, how are we in time? Oh, we still have, well, about 15 minutes left, so. Yeah, I'll just move on then. Well, just catch your breath for a second. Right, so in this next section, I thought let's just put in some more random topics, a bit more philosophical topics around special member functions. Because if you've ever transitioned from C++ to another language, or perhaps you already know multiple languages quite well, then you will get into this situation where, hey, where do I put this code that I was going to put in the constructor, but there's no constructor in this language. So like C++ and Java, I think C# as well, they have these concepts of these special member functions on types. And they at some point they will feel completely natural to us. And we always think in terms of these things. But that's not the case for all languages. If you go to another language, like Rust, for instance, they don't have these special member functions, but they must surely be able to deal with all these concepts, right? I mean, how would I be able to do object-oriented programming in these languages at all? Well, it turns out that at least from what I know of it is they made them such that they are not as tightly integrated with the types themselves. So they basically see them as a sort of additional luxury that you can put on there later on. For instance, if you look at Rust, for instance, they deal with class types completely different. Of course, I think Rust is not catered towards object-oriented programming as strongly as C++ is, but it still allows you to do object-oriented programming, as C++ also allows you to do functional programming. But how they do it is something like this. So we have some kind of module in which some parts of objects are public and some are not. And then through that, they basically allow you to do things or to not see things. And the pattern that they use, at least for construction, is something like a new function, so more like a factory method or a create function. And it's more like a convention, really, than a rule. So in this case, we basically have to create a new function that will generate an object of our type that we want. So that's construction. But how then do move and copy operations work? Well, in Rust, the semantics are the other way around. So the default semantics are move semantics. So we get a move like this, and we get a copy, or a deep copy, it is, a clone like this. But then how do we define the clone operations? Well, in this case, I made it easy for myself because the clone operation is basically like default generated by using these derived macros. But that's the way they do it. And then we have destruction, which is also possible to lean into in Rust, and that works with a trait called drop. And basically what will happen is once a still alive type goes out of scope, the drop function will be called. So you're still able to do almost everything, but they don't have like this intrinsic special member function stuff going on for each of their types. And it is also possible that in C++ you sometimes see things like this. And one of the patterns from the Gang of Four, the reusable, I don't know what the real title of the book is, but one of the patterns book that everyone knows. There's a pattern called factory method where you basically create a convention of a factory method on each type, where a superclass can basically call this method called create in this case on each type, and then have the type itself define how it is created. So what you then do is perhaps hide the explicit constructor and then force the user to always use the create function. But it does actually make sense to use this from another perspective, which is if you implement a normal constructor, you don't have a return value, right? So if you want a constructor to fail, what are the options? Well, you can like keep some kind of state and then have the user check this state later on, but that's a bit error prone because if they forget to check it, then the bad things can happen perhaps later on. So the most natural way in C++ would be to throw an exception. But perhaps exceptions are not really your favorite thing, or you're not even allowed to use them because it's sometimes the case. Then what can you do? Well, then only option one remains, which is a bit ugly. So in that case, it could make sense to do something like this. And now, basically, your constructed object is your return value. But this, this is not really nice for error handling again, because now what can we do here? Well, we could use something like a standard expected from C++23 and create a separate result type like this, and then have the result indicate whether or not the construction succeeded or not. Right? And now you can do all kinds of other things with that. So it does make sense to use this. Yeah. Right. So for the next couple of slides, I'm going to digress just a little bit more. I hope at least it will be useful for someone, because what we'll do is we'll look at some practical example of creating a class relationship while taking into account like an error-prone design or an error-less prone design. So we'll try to keep the design foolproof and then migrate it over refactorings. So we start out with a simple setup. So we're asked to implement an algorithm class that takes some kind of a configuration set and then internally initializes a resource with parts of the settings and also use part of the settings for the algorithm itself. This is a case, at least in my job, I encountered quite a lot. And like the initial requirements are really simple, but then over time, the class changes and things become a mess. So how can we prevent things from becoming a mess? Now, as I said, like the constructor of the algorithm class is responsible for like spreading the settings out to the resource and itself. So the way it works in version 1 is we basically have this bag of data. It's called configuration. It has some settings on board, and we basically ingest the settings in our algorithm right here, and then initialize the resource with some of the settings and initialize ourselves with the settings. And in this case, I chose to throw an exception if the configuration is bad. And this version 1 is called hard to use. And why is it hard to use? Because it's impossible to create an algorithm class with bad settings. Because if we somehow mess up this configuration set, it will fail during construction, and we won't even have an object or a handle to an object to call run on. So this is the most foolproof design that you can make. And it's really simple. But that's always how our class design starts, right? You have simple requirements, everything's nice, the grass is green, and then your colleagues and all the projects change, and we get new requirements, and all that. Things become more complicated. Because one of the drawbacks of this design here is that we can do like reconfiguration with different settings. So that's one of the requirements that we get. And also another requirement is that we can split like the default construction of this algorithm class and the initialization, because well, in my area we use GPUs a lot, and if you have a GPU and you do the first round of processing, it often takes some time to set up because it has to load drivers, or I'm not really sure what's happening in the background. But the first run always takes a very long time. So perhaps you want to split like initialization from construction. So then we go on and we change the code, and we end up with something like this. So we have our configuration again, the algorithm, and then we initialize. So first we basically construct the algorithm, and then we initialize it, and then we run on it. But as you can see, we are already left with a handle to an algorithm that is not initialized yet, and where we could call the run function on. So this already poses some difficulty. So now inside of this run function, we have to check whether or not our class was initialized. So things are becoming more and more complicated, and you can already feel where this goes. If you have 2 or 3 of these like complication iterations, things really become a mess if you have to keep a lot of administration in sync. So perhaps we'll change it even up more, and the next requirement is we add reinitialization support. So sometimes we want to run with one configuration, and then another time we want to run with another configuration, but we want to keep the original algorithm configuration around, or the class, the handle. How do we do that then? Well, things become more complicated. At least we reshape the initialize function such that it can be called multiple times. At least it will not run on invalid configurations. And what I added here as well was resource locking. So I added a mutex just to make sure that in a multi-threaded context we don't collide in the run function when writing to the code or to the resource. But if you think about this, this is often what I see classes like digress into. So they change, and at some point they become like really complicated administration systems with state and stuff. Couldn't we just like move the problem to another abstraction level, like so, and just go back to version 1, which was really simple, and just make the whole reinitialization thing an issue of a higher abstraction level? And this is sometimes the solution, but it's a solution that's often overlooked because people are really into this class and changing all the nitty-gritty little things because the added requirements seem like a small change from the previous requirement. But they don't think about whether they could even simplify everything, because now, again, we're unable to make an object that we can call run on when it's in an invalid state. So this is the best version, but we moved the problem of reallocation to another level. But of course, this is not always possible if you have to like throw away all your GPU initialization stuff every time. Perhaps this is not the best solution, so you have to split it up again. Another solution that I saw once is this one. It won't be long anymore, by the way, so just hold on for a couple of minutes. Is this version where we basically take apart our algorithm class into separate stages. And in this case, it's a bit silly because we only have 2 stages, otherwise my code wouldn't fit on the screen. But we have 2 stages, which is the initialization state and the run state. And each of those states only has the member functions that make sense for those stages. So we have the initialize member function on the, not even, on the algorithm init. So we can only create the algorithm init state if we have a valid configuration. And once it's there, we can use that to initialize a full algorithm run state. And that one has the run function. So we cannot call run on an init class. And basically by design, we rule out some error classes of use before init and stuff like that. This is a much more verbose solution, but well, I guess it makes sense in some situations. And of course, add more stages as needed. Right, now, that brings me to the end of my presentation. I would like to thank, of course, Howard Hinnant for his excellent work and resources, and also Jonathan Muller. Blocky is here. I can thank him in person. And of course, also Compiler Explorer team. Thank you for all the stuff. And thank you very much for being here.